что φ и L равно нулю. Да, φ в нуле и φ в нуле. Значит, это уходит в ноль, но, честно, потом еще несколько дифференцируем к такому виду. Но СК у нас просто появляется лишь множить вот это, но оно имеет такой вид. Схожий. Тогда мы утверждаем то, что... Сейчас, стоп, сейчас я скажу. Мы еще требуем, чтобы у них был компактный носитель. Да, мы требуем, чтобы у них был компактный носитель, и тогда мы говорим, что эти...
In the previous lecture we introduced the main notions of the theory of commutative Banach algebras, namely the maximal spectrum and the Gelfand transform. So far, we did it in the unital case. So today, our first goal will be to extend these notions, that is the maximal spectrum and the Gelfand transform, to non-unital Banach algebras. This is rather important because we remember that the algebras we are mostly interested in, namely the group L1 Banach algebras, are usually non-unit. To begin with, let's discuss a standard and simple procedure of adjoining an identity to a non-unital algebra. The procedure is called unitization. Suppose we have an algebra. Algebra is usual over the complex numbers, and as usual is not assumed to be unital. We denote by A plus the vector space direct sum of A, and the one-dimensional space spanned by a single element denoted by 1 plus. This is just a vector space direct sum. Then we introduce a multiplication on the space. Multiplication on A plus. We define it in such a way that this new element will be an identity for this multiplication. And there is the only reasonable way of doing this, namely you have two elements of this space, A plus, when we define their product just by this formula, AB plus lambda B plus A plus lambda mu 1. We just use the requirement that this new element 1 should be an identity. And it's very easy to check that this multiplication is associative, so it makes A plus into a unital algebra. A plus becomes a unital algebra. A unital algebra. And this algebra is called the unitization of A. A plus is the unitization. The unitization has the following simple universal property. The following proposition. Well, let's call it proposition exercise 1. If we have an algebra A and a unital algebra B, and suppose I have an algebra homomorphism phi from A to B. Let's define a new map phi plus, which acts from A plus to B, by the following formula, it takes A plus lambda 1 to phi of A plus lambda times the identity of B. This is phi plus. So clearly phi plus extends phi, and this is obviously a linear map, but it's also very easy to show that it is multiplicative, so it is a unital algebra homomorphism. Phi plus is a unital algebra homomorphism. And moreover, so this is statement 1 and statement 2, we have a natural bijection. There is a natural bijection between the set of all algebra homomorphisms from A to B and the set of all unital algebra homomorphisms, from A plus to B. Explicitly, we have an algebra homomorphism phi from A to B. Then this bijection takes phi to phi plus, where phi plus is defined here. And the inverse mapping is just the restriction map. If psi acts from A plus to B, we can simply restrict it to A. And this is a one-to-one correspondence. So these two maps are bijections, and they are inverse to each other. So this is the universal property of the unitization. And in fact, this construction easily extends to the case of Banach algebras. This is position exercise 2. Suppose now that A is a Banach algebra. Then, first of all, I explained that A plus is also a Banach algebra. With respect to the following norm. So we define the norm on A plus by the following formula. This will be the norm of A plus the absolute value of lambda. So the unitization of a Banach algebra is also a Banach algebra. And we will have a complete analog of proposition 1. That is, proposition 1 holds if we replace algebra homomorphisms by continuous algebra homomorphisms. So it holds for Banach algebras. With the convention that hom stands for the set of all continuous algebra homomorphisms. So the universal property of the unitization explained here extends literally to the case of Banach algebras. This is more or less immediate from the definition of this norm. Okay, by the way, here's a simple corollary. If you could have a character, if A is a Banach algebra, and chi is a character of A, then chi is automatically continuous, and the norm of chi is less than or equal to 1. Well, indeed, so at the previous lecture, or maybe 2 lectures ago, we proved this for unital Banach algebras. But by using the unitization procedure, we can easily extend it to arbitrary Banach algebras. Namely, if we take a character, then we extend it to A plus by using this proposition. We get a character of A plus, and it is bounded and satisfies this condition. Okay. Well, here's an example. Which shows how the unitization looks like in a very concrete special case. So suppose that X is locally compact. Locally compact. Oops, just a moment. X is a locally compact Hausdorff topological space. And let X plus denote the one-point compactification of X. Well, let's recall that as a set, X plus is just the disjoint union of X and a single point denoted like this. And the topology on X plus is defined as follows. First, we take all open subsets of X, and they, by definition, they will be open in X plus. And also we consider neighborhoods of infinity, which are defined as follows. They are complements in X plus of compact subsets of X. So this is the standard topology on X plus. And it's a standard fact. Actually, we have two facts. The first fact is that X plus is compact and Hausdorff. X plus is compact and Hausdorff. And now we have the following uniqueness result, which roughly says that this is essentially the only way of adding a single point to X to make it compact. More exactly, if we have a compact Hausdorff topological space Y, compact Hausdorff topological space, and if X is obtained from Y by removing a point, say Y0, then X is locally compact. And we have a homomorphism between the one-point compactification of X and Y. There is a homomorphism from X plus to Y, which takes every point in X to itself. Every point in X goes to itself, and infinity goes to Y0. So this simple result shows that this is the only, up to homomorphism, this is the only compact Hausdorff space which contains X and is obtained from X by adding a single point. Well, how is this related to the unitization? Well, here's an exercise for you. First of all, I claim that if we look at the algebra C0 of X, of continuous and vanishing ad infinity functions on X, then this algebra consists exactly of those continuous functions, or more exactly of the restrictions to X of those continuous functions of X plus, which vanish at infinity. In other words, a continuous function on X vanishes at infinity, in the sense of our previous definition, even only if it vanishes at infinity, literally. And by using this formula, we can easily show that there is a topological isomorphism, topological algebra isomorphism, between the unitization of C0 of X, the unitization of C0 of x, and the algebra of continuous functions on the one-point compactification, which takes every element in the unitization, f plus lambda 1, to f plus lambda, where lambda is considered as a constant function on x plus. Of course, here we assume that f is extended by 0 to infinity. I don't claim that this isomorphism is isometric. In general, this is not true. But on the other hand, we will see shortly that there is another standard way of defining an equivalent norm on C0 on the unitization of C-star algebra. If we introduce this C-star norm on this algebra, then this isomorphism will be isometric. Okay.
А это топологическая алгебра, говорите, да? В смысле, что?
Топологический изоморфизм алгебры.
Все.
То есть он и изоморфизм алгебры, и топологию уважает. То есть изоморфизм их как набежных пространств, банковых пространств. So I mean that this is just an algebra isomorphism which preserves the topology. An algebra isomorphism and homomorphism at the same time. It is not necessarily isometric, but it is a topological isomorphism. Okay. Now let's now extend the notion of the spectrum of an element of an algebra to the non-unital case. So again, we take an arbitrary algebra A over the complex numbers and an element little a in A. And we define the non-unital spectrum, of little a as follows. This is a subset of the complex plane, which will be denoted by sigma prime of A. And the definition is very simple. We define it to be the spectrum of A in the unitization of A. Well, a natural question is, what happens if A is already unital? Does the spectrum agree with the usual spectrum of A? Well, in general, the answer is no, because of the following observation. Let's observe that A is always a two-sided ideal in its unitization. Is a two-sided ideal. So little a, which sits in A, is not invertible. Is not invertible in A plus. An element of an ideal is never invertible. And so as a result, we deduce that the non-unital spectrum always contains 0. Always contains 0. Of course, if A is already unital, then the usual spectrum of A doesn't necessarily contain 0. But it turns out that this point is the only difference between the spectrum and the non-unital spectrum. And this follows from our next exercise. First of all, you have two unital algebras, A1 and A2, unital algebras, and little a is an element of their direct sum plus A1 plus A2. So we consider the direct sum as an algebra in the natural way, in the standard way. Then the spectrum of A is just the union of the spectrum of A1 and the spectrum of A2. This is almost immediate from the fact that this element is invertible in the direct sum, even only if both A1 and A2 are invertible. The second observation, the second exercise, is that if A is a unital algebra, then what can I say about its unitization? I claim that there is an algebra isomorphism between the unitization of A and the direct sum of A and the complex numbers, which takes every element in this direct sum, each pair A and lambda, to A plus lambda 1. Does it look reasonable? It looks reasonable, but this is not correct. This map is clearly a vector space isomorphism, just by the by the definition of the direct sum. But this map is not multiplicative. And to make it into an algebra isomorphism, we must replace here the identity of A plus by the following element. So we take the difference of two identities of A plus and A. And this is an algebra isomorphism. This is an algebra isomorphism. Well, the verification is straightforward, just with a little calculation. This somehow this result can be seen as an algebraic analog of the fact that if we have a compact topological space, a compact Hausdorff topological space, what can we say about the one-point compactification? The one-point compactification of a space which is already compact is just the disjoint union of two topological spaces. So the infinity will be an isolated point. And this is somehow looks like an algebraic form of this result. And if we now combine 1 and 2, we get the following. If A is a unital algebra and little a is an element of A, then the non-unital spectrum of A is the union of the spectrum of A and 0. So, in summary, if A is already unital, then the only difference between the spectrum and the non-unital spectrum is 0. So these two spectra are almost the same, modulo this single point. Okay, we can now extend, by using this formula, we can now easily extend the notion of spectral radius to non-unital Banach algebras. Suppose now that A is a Banach algebra, not necessarily unital, and little a is an element of A. And we define the spectral radius, of A, exactly as in the unital case, with the only difference that we replace the spectrum by the non-unital spectrum. So now lambda runs over the non-unital spectrum of A. And by looking at this formula, we see that if A is already unital, then this definition agrees with our previous definition of the spectral radius, because if I remove the prime here, the supremum will be the same. Exactly because of this formula. So this is compatible with the usual spectrum in the case where A is unital. And of course we have the same Berlin-Gelfand formula for the spectral radius. The spectral radius of A is equal to the following limit. Or we can replace the limit by the infimum. There is nothing to prove here because the inclusion of A into A plus is isometric, so we simply consider the same element as an element of A plus and apply the unital version of the Berlin-Gelfand formula. Okay, let's now look at non-unital versions of the maximal spectrum and the Griffon transform. Maximal spectrum and Griffon transform gamma for non-unital commutative Banach algebras. Well, let's start with the maximal ideals. It turns out that in the non-unital case, maximal ideals are no longer relevant. It's reasonable to consider only those maximal ideals which have a special property. So now if A is an algebra, and if we have an ideal, A, of course, now we assume that A is commutative. A is a commutative algebra. And if we have an ideal, I of A, we say that I is a modular. I is a modular, or some people say regular, if the quotient of A modulo I is unital. Explicitly, if we write this down explicitly in terms of A, this means that there is an element, U, in A, such that for every element A in A minus A U belongs to I. This means that U is an identity modulo I. And this element is called a modular identity. A modular identity for I. Clearly it is unique modulo I, because the identity in the quotient is unique. Well, here are some simple observations related to this definition. First of all, the zero ideal of A is modular if and only if A is unital. This is immediate from the definition. And of course, in this case, all ideals of A are modular. All ideals of A are modular. Also, if we have a modular ideal, I, then any larger ideal will also be modular. You have two ideals I and J. And I is modular. Then J is also modular. J is also modular. And clearly, a modular identity for I will also be a modular identity for J. If this is true for I, then the same inclusion is true for J. Observation 3 is that if we take a character, if Chi is a character of A, then its kernel is always a modular ideal. Well, indeed, if Chi is 0, then the kernel of Chi is just A, and clearly it is modular. And if Chi is not 0, then it is surjective. Then it is surjective, and so the quotient of A modulo the kernel is isomorphic to the complex numbers. But the complex numbers, of course, is a unit of algebra. And observation 4 gives us some way to produce counterexamples. That is, examples of ideals which are not modular. Let A squared denote the linear span of all elements of all products AB, where A and B run over A. And suppose that this is a proper subspace of A. Suppose A squared is not equal to A. Then each vector subspace, I, which sits in between A squared and A, such that A squared sits in I, and I sits in A, but I is strictly smaller than A, is a non-modular ideal. It's a non-modular ideal. Well, indeed, if we look at this chain, we see that the quotient of A modulo I, the multiplication in this quotient is identically 0. So this is a non-zero algebra with trivial multiplication. Clearly it is not unity. And there are many natural examples of such algebras. For example, we can take the algebra of polynomials with zero constant term. And we can take just A squared, which consists of those polynomials which start with T squared. So this is a proper non-modular ideal of it. Okay, now we define the maximal spectrum. The maximal spectrum of a non-unital algebra A. Spectrum. To be the set of all modular maximal ideals. Maximal modular ideals over here. Well, again, just like in the usual case, the natural question is it empty? Do we always have maximal modular ideals? And the answer is exactly the same as in the unital case. We have the following simple theorem, which states that each proper modular ideal, of A is contained in a maximal modular ideal. And the proof is exactly the same as in the unital case. It's almost the same. Modulo some details, which I leave as an exercise for you. So just as in the unital case, we applied Zorn's lemma. The only delicate point is to show that when we check that the conditions of Zorn's lemma are satisfied, that is, the condition that every chain is dominated by an element in the same set, we take the union of elements in this chain. And we have to check that this union is a proper ideal. And when we did it in the unital case, we used the assumption that A is unital. So we just apply the same argument, but we replace the identity of A by the modular ideal, by the modular identity for this proper modular ideal. And this works. By the way, for non-modular ideals, this is not true. There will be, so I'll make this exercise more concrete in the respective exercise sheet, but nevertheless, let me state it now that for this result fails for non-modular ideals. there are many natural counterexamples. So this is one of the main advantages of modular ideals. Okay, let's now come back to the maximal spectrum. Now we know that it is non-empty. And as in the unital case, let's also introduce the character space. This is another definition. The character space A. It is defined in exactly the same way as in the unital case. It consists of all non-zero characters. Instead of all non-zero characters of it. And exactly as in the unital case, we have an injection of a hat into the maximal spectrum. The map from a hat to the maximal spectrum, which takes every non-zero character to its kernel. And we have already observed that the kernel of a character is a maximal modular ideal. It is modular and it is maximal just because it has codimension 1. And this map is injective. This is a simple exercise for you. Okay, now.
А вот нулевой характер, он, получается, будет предыдущей компьютерификации, да? Если...
Ну, нулевой характер просто сюда не входит.
Нет, в смысле, вот есть его...
Я сейчас скажу. So far this set doesn't contain a zero character, but we will add it shortly to a hat. In fact, to work with these sets, it's convenient to enlarge them a little bit to add a single point. So, well, let's introduce some notation. We denote by a hat plus the set of all characters, including 0. All characters. So in other words, this is the union of a hat and the 0 character. And also we enlarge the maximal spectrum. We introduce the set max plus of A, which is the union of the maximal spectrum and the algebra A itself. So we consider A as an ideal in itself. So clearly we can extend this map to a hat plus, so that this 0 character goes to A itself under this map. And we have the following result of a proposition. So let's look at the following picture. We have the set. We can take the character space of the unitization of A. And restrict every non-zero character of A plus to A. And in this way, we get a map from here to A hat plus. So every character goes to its restriction to A. Also have a map from the maximal spectrum of the unitization of A to the set max plus of A, which takes every maximal ideal of A plus to its intersection with A. And this turns out to be maximal modular ideal of A, which is not entirely obvious, but I'll give you a little hint of how to prove this. And finally, we have two arrows from here to here. So both arrows take every character to its kernel. So the proposition states that the diagram commutes. The diagram commutes and moreover the horizontal arrows are bijections. The horizontal arrows are bijections. The proof is a useful algebraic exercise for you. In fact, well, the commutativity of the diagram is rather easy. In fact, the fact that the upper horizontal arrow is a bijection is also clear because it's just a special case of the universal property of the unitization. This is a special case of this formula. So if B is the complex numbers, then this bijection gives us what we want. So this is the set of all unital characters of A plus and the set of all characters of A. What is not entirely trivial here is to prove that the bottom horizontal arrow is, first of all, it is well defined, so it indeed takes this set to this set. In other words, this intersection is a maximal modular ideal, and that is bijective. And so here's a hint for you, which shows in particular which hints how to prove the surjectivity of this map. So we will start with a maximal modular, not necessarily maximal actually. The hint works for every modular ideal A. So if we have a modular ideal I of A, a modular ideal, and U is a modular identity for I, we can construct another ideal in the unitization as follows. We define J to be the direct sum of I and the one-dimensional space spanned by 1 plus minus U. And I claim, this is rather easy to check, that J is an ideal of A plus. Ideal of A plus, and the quotient of A plus modulo J is isomorphic to the quotient of A modulo I. In particular, this isomorphism implies that A is maximal if and only if J is maximal. So this is a field if and only if this is a field. And this hint shows how to prove the surjectivity of this map. We take maximal modular ideal of A, and we construct a maximal ideal of A by using this formula. Okay. Now we see that A is a Banach algebra. So we know that in the case of a Banach algebra, of a commutative Banach algebra, this arrow, the first vertical arrow, is also bijective. But the diagram is commutative, and this implies that the second vertical arrow is also bijective. So we obtain the following corollary. Suppose that A is a commutative Banach algebra. Then, first of all arrows in the diagram are bijective. Arrows in, well, is denoted by G. All arrows in the diagram G are bijections. we already know that this one and this one are bijective. We know that this is a bijection, and so this implies that this one is also bijection. A bijection. Second corollary is that all maximal modular ideals of A are closed in A. All maximal modular ideals of A are closed in A. Well, indeed, we know that all maximal ideals of A plus are closed in A plus. And of course, if I is closed in A plus, then the intersection of I and A is closed in A, in the induced topology. So since this is a bijection, we deduce that all maximal ideals of A are closed. All maximal modular ideals of A are closed. Non-modular ideals are not necessarily closed. They are very simple counterexamples. Just take an algebra with trivial multiplication. You will easily find there non-closed maximal ideals, which are not modular. And corollary 3 is that the canonical map from A hat to the maximal spectrum, which takes every character chi to its kernel, is bijective. Well, we simply restrict this bijection to non-zero characters, and we get this bijection. Okay. Let's now topologize the maximal spectrum of A. This is done exactly the same way, in exactly the same way as in the unital case. We define the Eagle-Font topology. On the maximal spectrum of A, which from now on will be canonically identified with a hat. And it will be also convenient to define the Eagle-Font topology on max plus of A, which is again canonically identified with A hat plus, to be the restriction of the weak star topology on A star. It's the restriction of the weak star topology on A star. So we know that A star contains all characters, that is, all characters are continuous. So the maximal spectrum becomes a topological space. And what can we say about this space? Well, we have the following proposition, which again is almost immediate from the unital case. First of all, both spaces max of A and max plus of A are Hausdorff, simply because the weak star topology is Hausdorff. Max plus of A is compact. Max plus of A is compact. And it is homomorphic to the maximal spectrum of the unitization of A. As for the maximal spectrum itself, it is locally compact. Max A is locally compact. And moreover, the space max plus of A is nothing but the one-point compactification of max of A. Well, indeed, why is it so? Well, I have already explained why they are Hausdorff. They are Hausdorff simply because a star is Hausdorff for the weak star topology. Max plus of A is compact. Just look at this diagram. So if we equip, if we topologize all spaces in this diagram, then this arrow will be, well, first of all, the vertical arrows will be homeomorphisms, just by definition. And this arrow will be a homeomorphism because this is obviously a continuous bijection between, from a compact Hausdorff space to another Hausdorff space. So it is a homeomorphism. So this is also a homeomorphism. And so in particular, this implies that this space is compact. Max of A is locally compact because it is because it is equal to max of A minus a single point. That is the ideal, which is equal to A itself. So it is locally compact, and for the same reason, max plus of A is the one-point compactification of max of A. So if A is unital, then this extra point is isolated, and both spaces are compact, max of A and max plus of A. But if A is not a unital, then this point is not isolated, and max of A is not compact. It is only locally compact. Okay, let's now introduce the Gaussian transform. As before, we assume that A is a commutative Banach algebra. And we define the Gaussian transform. The Gaussian transform of an element little a in A is a function A hat on the maximal spectrum, which is again identified with the character space. And the definition is exactly the same as in the unital case. So it is this function is given by the following formula. For all characters. So what can we say about this function? Well, I claim that it is continuous and vanishes at infinity. So it sits in the algebra C0 on the maximal spectrum. It is continuous and vanishes at infinity. Well, why is it so? The easiest way is to extend this function to max plus of A. Extend a hat to a function which will be denoted by the same symbol, A hat. It is now defined on max plus of A, and max plus of A, we identify max plus of A with A hat plus with a set of all characters, including 0. And we extend it by the same formula. This formula makes sense also in the case where k is 0. So a hat becomes a function on A hat plus. And it is continuous. A hat is continuous on A hat plus. This follows from the same argument as in the unital case. See the unital case. Basically, this property follows from a simple property of the weak star topology. This is the restriction of the canonical image of A in the bidual space. And elements in the bidual are continuous for the weak star topology. So it is continuous, and clearly it takes 0 to 0. But what is the 0 character? Well, after we, if we identify the maximal, the set A max plus of A with the one-point compactification of max of A, this is just infinity. This point is infinity in this one-point compactification. And to complete the proof, let's just look at Where is it? Just look here. So a hat becomes a function on the one-point compactification which vanishes at infinity, literally. And this means that actually this function belongs to C0 on the maximal spectrum. So a hat belongs to C0 on a hat. And this completes the proof. So now if we take every element in A to its Gelfand transform, we obtain a map from A to the algebra C0 on the maximal spectrum. And this map is called the Gelfand transform of our algebra. The Gelfand transform of A is a map gamma, which acts from A to the algebra C0 on the maximal spectrum of A, and it takes every element little a to the function A hat. How is this map related to the Gelfand transform of A? Well, the relation is given by the following picture. This is A. This is the unitization of A plus. So we look at the Gelfand transform of the unitization, gamma A plus, and it acts from A plus to the algebra of continuous functions on the maximal spectrum of A plus. But we still remember that we can identify the maximal spectrum of A plus with the space max plus of A by using this identification. And on the other hand, we have the Gelfand transform of A. Let's draw it here. It acts from A to C0 on the maximal spectrum. This is the Gelfand transform of A. So A is contained in its unitization. And again, we identify this algebra with the ideals of those continuous functions on max plus, which vanish at infinity, that is at the zero character. So it is an ideal in here. And the diagram commutes just by construction. Let's observe that the diagram commutes. This easily follows from the construction. And by using this diagram, we can easily transfer the basic properties of the Gelfand transform of A plus to the algebra A. And we get the following theorem. First of all, gamma A is an algebra homomorphism. This is true because gamma A plus is an algebra homomorphism. But of course, this is also true for trivial reasons. Second, the norm of the Gelfand transform of A is less than or equal to 1. Well, indeed, the Gelfand transform of the norm of gamma A plus is exactly 1. And this is the restriction of this map to A. Well, in general, I don't claim that this norm of this restriction is exactly 1. So we can produce examples where it is strictly less than 1. But in any case, this is less than or equal. This norm is less than or equal to 1. Property 3, for every element A in A, the supreme norm of A hat over the maximal spectrum is exactly the spectral radius of A. Well, this is true because this is true for the Gelfand transform of A plus. So we simply restrict, we use this diagram, and we get this equality. Property 4, for every A in A, the non-unital spectrum of A is almost the range of a hat. More exactly, we have to take the union of the set and 0. And again, this is true because this is true for a plus. This is equal to the spectrum of little a in a plus. And if we extend a hat trivially to max plus away, we get this set. So we add 0, which is a hat evaluated at infinity, and we get this equality. And finally, the kernel of the Griffin transform is equal to the intersection of all maximal modular ideals. Maximal modular ideals of A. And this is the same as the set of all quasi-nilpotents. Okay, so these are main properties of the Griffin transform for not necessarily unital commutative Banach algebras. Okay, our next goal will be to prove, actually the proof will be given at the next lecture, one of the most fundamental results in the theory of C-star algebras, which is due to Griffin and Nymark, and which states that if A is a commutative C-star algebra, then the Griffin transform is actually an isometric star isomorphism between A and the algebra of continuous and vanishing at infinity functions on the maximal spectrum. Today we discuss some preparations with some preliminary results. So to begin with, let's discuss products and unitizations of C-star algebras. Of C-star algebras. Well, the situation with products is rather simple. So let's start with products. Well, it's rather easy to observe that if we have two Banach star algebras, say and B, A and B, are Banach star algebras, we can form the product, or equivalently direct sum, and I claim that their direct sum, or their product, is also a Banach star algebra. In the following natural way, we define the norm on, well, first let's define an involution, which is immediate. So if we have an element in the direct sum, and if we want to define their joint, the joint of this element, so the involution is defined in the following obvious way. This is the involution on the direct sum, and the norm, the natural norm, is the maximum norm. The norm of a pair AB is the maximum of the norm of A and the norm of B. And so A plus B becomes a Banach star algebra. And moreover, it's a very simple exercise to show that if A and B are C-star algebras, then so is the direct sum. The direct sum is also a C-star algebra with respect to this norm. The situation with unitization is more delicate. Again, let's start by observing that you have two Banach star algebras. Sorry, not two. We want to construct the unitization. So if we start with Banach star algebra, A is Banach star algebra, Then so is its unitization. Well, indeed, the involution on A plus is given by the only reasonable formula, which can be written down in this case. This is just A star plus lambda conjugate 1. And this is an involution on A plus, and let's recall that norm on A plus was defined to be sum of the norm of A and the absolute value of lambda. This is very easy. Now what happens if A is a C-star algebra? It would be reasonable to expect that A plus is also a C-star algebra. But unfortunately this is not the case. This is an exercise for you. If A is a non-zero C-star algebra, then this norm, let's denote it by 1, doesn't satisfy the C-star axiom. So it is not a C-star algebra. Luckily enough, it turns out that there is another way to define a norm on A plus and to make it into a C-star algebra. And the construction of the C-star norm on the unitization depends on whether or not A itself is unital. So let's start with the simple case where A is already unital. So suppose that A is a unital C-star algebra. So we know that in this case, A plus is isomorphic as an algebra to the direct sum of A and the one-dimensional ideals spanned by spanned by a certain element. I'll just write it this way, and let's recall how this isomorphism looks like. So it takes every element A lambda in the direct sum to A plus lambda times the difference of two identities. And this is an algebra isomorphism. But we already know that the product, the direct sum of two C-star algebras, is a C-star algebra. So we can now just take the C-star norm on here and move it to A plus. And so we deduce that A plus becomes a C-star algebra, becomes a C-star algebra with respect to the following norm, the norm of A plus lambda times the difference of two identities is the maximum of the norm of A and the absolute value of lambda. Or equivalently, we can write it as follows. The norm of A plus lambda 1 is the maximum of the norm of A plus lambda times the identity of A and the absolute value of lambda. So if A is a unital C-star algebra, then its unitization is also a unital C-star algebra with respect to this norm. Of course, a more interesting case is the case where A is not unital. And if it's not unital, then the C-star norm, the canonical C-star norm on its unitization, is given by the following proposition. Suppose that A is a strictly non-unital. When I say strictly, I mean that it doesn't contain an identity. C-star algebra. Strictly non-unital C-star algebra. Well, we know that A is an ideal in its unitization. And so for every element A in A plus, we can consider the multiplication map LA, which acts from A to itself, and it takes B to AB. And we define a norm of A. I'll use the following notation for this norm to be the operator norm of LA. The norm of this operator LA. That is explicitly, this is the supremum over the closed unit ball of the norms of all elements A, B, where B runs over the closed unit ball of A. I claim that, first of all, this is a norm. This is a norm on A plus. Second, this norm extends the original norm on A. So for every n A in A, the new norm is equal to the old norm. And finally, the unitization of A, equipped with this norm, is a C-star algebra. A C-star algebra. To prove this result, we start with property 2. First of all, we will show that this norm extends the original norm A. So far, we don't know if this is really a norm. Anyway, this is clearly semi-norm, and we will see shortly that this is indeed a norm. But first of all, let's see that it extends the norm A. Well, indeed, since the norm A is submultiplicative, so we clearly have the following inequality. And when we take the supremum over the unit ball, we deduce that the new norm on A is less than or equal to the old norm. But on the other hand, this inequality becomes into inequality if we substitute A star here. A star is, by the C-star axiom, this is the norm of A squared. And this is the same as the norm of A times the norm of A star. So if B equals A star, then this is an equality. And so actually the supremum is equal to the norm of A. So we deduce that these two numbers are the same. Let's now show that this is indeed a norm on A plus. So clearly this is a semi-norm. This is a semi-norm. Well, suppose that let's suppose that we have a non-zero element in the unitization. And suppose that its semi-norm is 0. So we want to get a contradiction. Well, what does that mean? This means that the multiplication operator LA is 0. Okay, so A is a non-zero element. Let's write it in the form B plus lambda 1. And observe that by property 2, lambda is non-zero. because if lambda is 0, then A equals B, so A little a sits in the original algebra A, but on A, the new norm and the old norm are the same. So this equality would imply that A is 0, but A is not 0. So if A is not 0, we necessarily have that lambda is not 0. On the other hand, by assumption, for every element C in A, AC is 0, because this multiplication map is 0. So what does that mean? This means that this is, we have BA plus BC plus lambda C is 0 for every C in A. This implies that minus lambda inverse B, C equals C. We simply divide by minus lambda, and we get this equality. In other words, this element in brackets is a left identity. That is an element, the element E, which is equal to minus lambda inverse B, is a left identity in A. If you now take the adjoint of this element, we easily see that E star, by using the axioms of the involution, we deduce that E star is a right identity. In A. But it's a simple algebraic exercise that if an algebra has a left identity and a right identity, then it is unital. A is unital, which is a contradiction. So because A was assumed to be strictly non-unital. Okay, so this shows that this new norm is indeed a norm, on A. So now we have to show that this is a C-star algebra. Oh, I see it's time to finish. So if you give me just a few minutes, I'll complete the proof. Is it okay for you?
Yes.
Oh, thank you. This is rather quick. Actually, almost everything follows from two simple lemmas, which I'll leave as exercises for you. Lemma 1 states that if we have we have a normed space, and E0 is a codimension 1 closed vector subspace, of codimension 1, actually we don't have to require that it is closed, it will be automatically closed. I call it a vector subspace of codimension 1, such that the quotient, such that E0 is a bound space. So I claim that if E0 is complete, then so is E. Will be automatically closed because it is assumed to be complete. Then so is E. This is a simple lemma from classical functional analysis. And lemma 2 is essentially algebraic. If A is a Banach star algebra, such that for every A in A, the following inequality holds. I claim that A is a C-star algebra. A is a C-star algebra. In other words, this inequality implies both the fact that the involution is isometric and the C-star equality. So if this inequality holds for every element in A, then actually it is an equality. So these numbers are actually the same. It's a simple algebraic exercise, just a little calculation. A couple of lines. Okay, let's now prove part 3. So these numbers are exercises for you. So we want to show that A plus is a sister algebra. First of all, lemma 1 implies that it is complete. By lemma 1, A plus is a Banach algebra. So clearly this norm class is submultiplicative. So it is a normed algebra. The operator norm is submultiplicative. So it is a normed algebra, and it contains A as a codimensional subspace. But A is complete, and so A plus is also complete. And to prove that it is a sister algebra, actually it's a Banach star algebra, because the evolution is sorry. Actually, this we can prove that the evolution is isometric directly, but the easiest way is to modify slightly lemma 2. Now let's modify it as follows. If A is a Banach algebra equipped with an involution, so what is essential here is that I don't assume that the involution is isometric. We don't assume that the involution is isometric. We only assume that this inequality holds. And this inequality, in fact, implies the fact that the involution is isometric. So applying this lemma, we deduce that A is a Banach algebra. And to prove that it's a sister algebra, we have to check this inequality. Well, let's take an element A in A plus. We'll take an element B in A. And let's look at the norm of the following element, AB squared, which appears in the definition of the norm of A. So what is this? This is, A is a sister algebra. Since A is a sister algebra, we can use the C star axiom here. This will be equal to AB star AB. This is, what is this? This can be written as B star A star AB. And by the submultiplicativity of the norm in A, so B star sits in A, this element is also in A. And so this is equal to the norm of B star times the norm of the element A star A B. Now we use so this element sits in A plus, and we use the definition of the norm on A plus, and by the definition of this norm, this is less than or equal to the norm of B star times the norm of A star A. Now we take the operator norm on A plus times the norm of B. So in summary, we get the norm of A star A times the norm of B squared. So we now look here, and we take the supremum over the closed unit ball of A. So B now runs over the closed unit ball of A. We take the supremum, and we deduce that the norm of A squared, this is the norm in the unitization, is less than or equal to the norm of the element A star A. In other words, we have this inequality in A plus, and by using lemma 2, we deduce that A plus is a sister algebra. A plus is a sister algebra. And this completes the proof. Well, in summary, we see that this result can lead to some dissatisfaction because the norm on A plus is defined in two completely different ways, depending on whether or not A itself is unital or not. In the unital case, we have one construction. In the non-unital case, we have a completely different construction of the norm. But we will see shortly, this will be done at the beginning of the next lecture, that if a star algebra has a C star norm, that is, more exactly, if there is a norm norm on a star algebra which makes it into a C-star algebra, then this norm is unique. In other words, there is at most one norm on a star algebra which makes it into a C-star algebra. And therefore, the norm on the class that we've just constructed is unique. So the construction is different depending on whether or not the algebra is unital, but the norm is necessarily unique. So in some sense, it is canonical. Okay, so that's all for today. At the next lecture, we will discuss some important spectral properties of C-star algebras. And we deduce, from the properties, we deduce the Grafant-Nairac theorem, which states that the Grafant transform of a commutative C-star algebra is an isometric star isomorphism.